I'm sure you already know what GPS is, but have you ever wondered how GPS actually calculates your position, or what sort of limitations there are to its accuracy? In its most basic form, GPS triangulates your position by measuring how far away it is from different satellites. It knows the position of each satellite, and by drawing an imaginary ring around each one, it can calculate its position as the point where all the rings intersect. It sounds simple enough, but in this video we're going to explore exactly how it measures that distance and what sort of errors can creep in throughout the process. Let's look at this diagram. To keep things simple, I'm going to only work on a 2D image. For 3D, like in real life, you just need to add an extra satellite to work out the extra dimension. This satellite will broadcast its code at a set time. Let's call that time t=0. The transmission will travel out from the satellite at the speed of light. Obviously I've slowed it down here. As it travels out, time ticks away. At time t=5, the receiver picks up the signal. If the time on the receiver and the time on the satellite were perfectly in sync, the receiver could easily calculate the precise distance to the satellite using the equation distance equals speed times time. Time was measured at 5, and the speed is the speed of light. With that distance, it can draw a ring around the satellite and know that it is somewhere along that ring. Repeating the process with a second satellite gives us a second ring. The GPS knows it is at the location where the two rings intersect. You'll notice that there are 2 points where these circles intersect, but if we add in the additional restraint that the position has to be near the surface of the Earth, then we can eliminate one of those points. Of course, all this only works if the receiver and the satellites keep perfect time. For the satellites, that's easy. Each one carries multiple atomic clocks. Atomic clocks use the atomic oscillations of atoms to maintain time accurate to within less than a second over millions of years. This sort of accuracy is necessary when you consider that the signal travels at the speed of light, which is 300,000 kilometers per second. If time was out by as little as 1 second, the position would be 300,000 kilometers away from where it should be. GPS receivers, however, do not have built-in atomic clocks. They've only got normal clocks, which are nowhere near as accurate as is needed. What this means is that instead of knowing the precise time, as is kept by the satellites, they have their estimated time, based on their own clock. To turn this into the same precise time that the satellites use, they need to apply an unknown offset. In our previous example, instead of the receiver knowing that the time equals 5, it would now think that the time equals 5 plus some offset, which we're just going to call alpha for now. The equations that we use to calculate the distance to the satellites now becomes distance equals speed times time, which equals speed times 5 plus alpha. This offset is going to be the same for all equations, as the time offset is constant. The receiver's clock is wrong by a set amount. We just don't know what that amount is. With the additional unknown, it's no longer possible to find our position using only 2 satellites. 2 satellites worked when we needed 2 unknowns, our x and our y coordinate. Now that we have 3 unknowns, x, y and alpha, we need 3 satellites to solve the required equations. Of course, we've only been working in 2 dimensions so far. In real life, there is an additional dimension. We'd actually want latitude, longitude, altitude and time. The same principle applies, which just means we need 4 satellites to produce enough simultaneous equations. It is this reason that GPS receivers all lock onto a minimum of 4 satellites before they're able to give you your position. Even after completing all these calculations, there are still limitations and errors that can creep in. Propagation. These are errors that arise due to signals from satellites slowing down as they pass through different layers of the atmosphere. Different atmospheric layers are made of different elements, creating different densities. As signals pass through these layers, the speed at which they travel might reduce slightly. Normally, GPS signals travel at the speed of light, but if they slow down in places, they're going to take longer than expected to reach the receiver. This results in a slightly erroneous measurement of pseudo-range to the satellite, which results in slight inaccuracies to the final calculated position. Remember, we've already said that for every second of error our position is out by 300,000 kilometers. 1/1,000,000th of a second is going to result in an accuracy of 300 meters, which is still way bigger than we need. GPS can compensate for some propagation errors by transmitting a second signal at a different frequency to the first. Different frequencies are disrupted differently when passing through layers of the atmosphere. Comparing the second frequency to the original gives enough information to work out a correction to apply. Multipath errors are caused by signals from satellites not taking a direct path to the receiver. Maybe they bounce off a building or a cliff face before reaching the receiver. Again, this results in the signal taking a longer time to reach the receiver than it would have taken if it had travelled along the direct route. Again, this results in an erroneous distance being calculated. In terms of marine GPS units, these errors are not so common. There are not so many structures at sea that result in multipath errors, and GPS aerials are placed high up on the ship's superstructure, improving the visibility of satellites. Ephemeris or orbital errors are due to slight variations in satellite orbits. If the orbit was precise, all the numbers would tie in perfectly. As the orbit of the satellites varies slightly, small errors can creep into the calculated positions. Ephemeris errors are correctable because satellite positions are observed by ground stations. Ground stations calculate the difference between the satellite's expected position and their actual position, so they can apply the correction. Receiver noise refers to errors resulting from electronic signals within the GPS receiver unit itself. The receiver is a small level of interference, much like the static you can sometimes see on your TV screen. This can affect the signals received and in turn affects the calculated pseudo-ranges to each of the satellites. A lot of this can be solved with just quality of equipment. You generally find more expensive equipment will suffer from less noise. Relativistic errors are errors that result from relativistic effects within the satellites themselves. There are loads of videos about Einstein's theory of relativity, but the part we're interested in is the part that describes how time runs at different speeds depending on the relative speed between two observers. This is important for us because satellites orbiting the Earth travel so much faster than observers on the Earth, about 9,000 miles per hour. Time on each satellite appears to run differently to time on Earth. On satellites, it actually runs slightly faster, so all the clocks will be turning that little bit quicker. To compensate for this, the clocks are programmed to run slightly slower than they would do on Earth. From the point of view of an observer on Earth, the clock is actually running at the right speed. Relativistic effects are still monitored from stations on Earth to ensure the system maintains its accuracy. And finally, differential GPS. Now, differential GPS was a system originally developed to combat selective availability. Selective availability degraded the accuracy of signals randomly. It made positional accuracy less precise for users that were not part of the US military and did not have access to the key to decode the errors. The theory behind DGPS was that you could build a receiver in a fixed location and compare its GPS position to its actual position. The difference between the two was due to selective availability. The difference could be broadcast as a correction to all receivers in the area that were equipped to receive DGPS corrections. The correction effectively eliminated selective availability, contributing to its eventual termination. Today, even though selective availability is no longer an issue, DGPS is still used to provide corrections to GPS signals and increase its overall accuracy. And that brings us to the end of today's video. If you've enjoyed the content, this video is actually based on an article that I've written for my new website. I'm going to add the link down in the description below. Otherwise, hopefully you've found the content interesting. Until next time, thank you for watching, and goodbye.